All right, today we're going to work on Module 19.3, Properties of Rotations. We've already worked with translations and reflections. Rotation is just a little step up from there. So a rotation is a transformation that turns a figure around a given point called the center of rotation. The image has the same size and same shape as the pre-image, so that will not change. All that's moving in a rotation, like you can think of it, this wind turbine, or think of it like a windmill, think of it like anything that rotates really, a clock, the hands on the clock, it is just going to be moving location, not size or shape. So I trace the triangle that's here, triangle ABC. I'm going to use it to help me rotate this triangle at its center of rotation, which in this case is going to be the origin. So it says trace triangle ABC onto a piece of paper and cut it out. Rotate your triangle 90 degrees counterclockwise about the origin. The side of the triangle that lies along the x-axis should now lie along the y-axis. So if I take this triangle and I rotate it counterclockwise, meaning the opposite of the rotation of a clock, 90 degrees is just going to be one quadrant over. 90 degrees. And what needs to happen as I'm rotating this is that this point of origin, A, is going to continue to stay on A. That is not going to move. So I'm not changing it from this location, moving it over, and then rotating and it ends up somewhere else. No. This point never leaves the origin because that is my center of rotation, is the origin, it tells me. So I'm going to continue to rotate it so that this entire triangle rotates 90 degrees, not just this one point, right? And because this side AB is laying on the x-axis, my next rotation of it should be for it to lie on another line, in this case, the y-axis. So that point A didn't move, and this side length didn't change. All that happened is I moved the side from the x-axis to the y-axis 90 degrees. I can tell it's 90 degrees also because now I've created a 90-degree angle with my triangle. So I'm going to trace this triangle, right? It's not the perfect size, but this is going to be called A prime, right? This point B moved right here, B prime, and this longer point C is going to be C prime, right? Now it says sketch the image of the rotation, label them as A, B, C prime. Describe the motion modeled by the rotation. Well, all I did was rotate it how many degrees? 90 degrees. And in which direction? Clockwise would be this way, counterclockwise that way. So I did counterclockwise. Right? Awesome. If I were to go ahead and rotate it clockwise though, what if I rotated it clockwise? This is counter, and this is clockwise. If I were to rotate it 90 degrees this way, right, my point of origin A would still not change, but what would need to happen is for this line AB now would need to lie over here. So I would rotate 90 degrees, and my triangle now sits flat, like that. And you can tell it's 90 degrees because, again, I've created a 90-degree angle. Each of these quadrants is another 90 degrees of rotation. So this would be my 90-degree rotation in this case. If I went one more quadrant, we'd be on a straight line again. So it would be 180 degrees now that we've made. Another 90 degrees would be 270 degrees. And back to its original spot would be, you guessed it, 360 degrees. Like a full circle, right? Same thing clockwise. It's just going the opposite direction, but it's still every quadrant 90 degrees. Here's our 90-degree rotation clockwise, 180-degree rotation clockwise, 270, back to its original spot, 360. So think of it that way. Every quadrant, 90 degrees. Okay, that's very helpful to remember. We'll go ahead and skip the trapezoid investigation because we're not going to do the measuring of the lengths and angles, because we know that in this rotation, like we were told earlier, the size and the shape does not change. And like you saw here with these triangles rotating, the size, the lengths of the triangles didn't change either. Neither did their degree measurements, their angles, right? So the size and shape doesn't change. The only thing that changes is its location. So we're going to try that now, okay? And we're going to talk about congruency too. So congruency means having one image, in this case the pre-image, be congruent or exactly the same size, exactly the same shape, exactly the same degree measurement as the new image we would create. So in order to enlarge this and help you see it a little bit better, because now we're working with a triangle that's in a couple of different locations and quadrants, I'm going to draw it over here for myself. So I will draw a coordinate grid like we have in our book. Okay, and in this case, triangle, this is going to be 1, 2, 4, 6, 8, and my measurements on this side also go by 2, so 2, 4, 6, 8, and 2 in this direction, -2, -4, -6, and then 2 in the bottom, -2, -4, -6. All right, I will use another color to draw the original triangle that we're given. In this case, it's triangle ABC, where A is on the point of origin, C is at 2, 3, so 2, 3 for C, A, and then B is at -2, 3, -2, 3 for B. And I'll connect my triangle and let you see it. Okay, just like we have in our book. So it says, graph the image of the triangle ABC after a rotation of 90 degrees clockwise. So rotate the figure clockwise from the y-axis to the x-axis. Point A still stays at 0, 0 because that's our point of origin. So that point does not change. However, now we have to measure how do we change the other points. So 90 degrees clockwise. Clockwise is going to be in this direction. Okay. We are going to have to keep in mind A is going to stay the same. It's at the origin. But point B, I want to, and point C really, but let's start with B. I want to be able to transfer it 90 degrees clockwise, knowing that it's going to end up now in this quadrant because every 90 degrees the points move a quadrant. So 90 degrees for B would be 1 quadrant over. Okay. So in order to find out where this point is going to go in this quadrant, I need to really see the distances from the y-axis and the x-axis. Here I have a distance of 2 from the x-axis and a distance of 3 on the y-axis. Well, now that that's rotating and changing, I am going to now be a distance of 2 along the y-axis, height-wise, and a distance of 3 on x. So my new point is going to be right here, B prime. I still have a distance of 2, which now transferred over, flipped, right, from the distance on x to now the height of y, and a distance of 3, which now changed from the height of y to the length of x. So I'm kind of flip-flopping everything. Then C is also 2 spaces on the x-axis and a height of 3 on the y. So I'm going to flip those and make sure that C, since it's in this quadrant, a 90-degree change for it clockwise would mean it would need to end up in this quadrant. And since C is a distance of 4 away from B, I can literally just count 2, 4 to figure out that C is going to be right there. Let me erase all these Let me erase all of these extra markings to kind of help you visualize it a little better so that there's not too much going on. Okay. All right. So what we did there to rotate it 90 degrees, A didn't change, but it did need to be in a new quadrant, right? It didn't need to change the triangle to a new quadrant. B was a distance of 2 away from Y. So we flipped it and said, okay, now it's going to be a distance of 2 height-wise from X. And then it was a height of 3. So now it's going to be a length of 3. We literally just flip-flopped its measurements. And we counted. B is 1, 2, 3, 4 units away from C. So instead of trying to figure out all the new coordinates for C, all I needed to do was count that same length down, because C prime needed to now be in this quadrant, right? It needed to switch a quadrant of 90 degrees over. Little confusing, but it's doable. All you need to remember is that each quadrant is going to take us 90 degrees in the opposite directions, clockwise or counterclockwise, and that every point needs to move along that same rotation. So you would count your distances from the x's and the y's, and you would make sure your lengths stay the same. This shape is now completely congruent. A distance of 4 from B to C in both places. The A is still at the origin. We still have a height of the triangle of 1, 2, 3, just like here, a height of 1, 2, 3. And we still have a length from B to this axis and C to this axis of 2 and 2, and a here 2 and 2. So the more you practice with rotations, the easier they'll get, obviously, and you just need to keep in mind that you're really counting to make sure that these triangles stay congruent. Okay, you're making sure that the lengths stay congruent, the heights stay congruent, and that the point of origin does not move, and that each new quadrant is 90 degrees in rotation. Let's try this on our own for number 6, 7, and 8. I want you guys to pause the video and try this by yourself and see where it takes you, and then you can come back to see what we do here. So go ahead and take a second to pause and then come back. If you've stayed on, or if you are back because you were confused or just want to see how you did, welcome back. Let's try to rotate for number 6, 180 degrees. Graph the image of quadrilateral A, B, C, D after each rotation. So it's telling me 180 degrees, but it's not saying clockwise or counterclockwise. In that case, it really doesn't matter. For 180 degrees, whether I go clockwise, 90 to 180, or counterclockwise, 90 to 180, I'm still going to get into the same quadrant. So I don't need to say clockwise or counterclockwise for 180 degrees, because it's going to be kind of like a reflection over the origin, okay, diagonally. So let's see how that takes us. This point A is going to stay the same. However, point B, we see that it has a height of 2 and a length of 1. We're going to do the same thing for the bottom. It's going to rotate 90, 180, and it should be a direct reflection of it. 2 for the height and 1 for the length. B should be right there. For D, D is going to rotate, if this is a length of 1, 2, 3 for D, it's going to rotate up 1, 2, 3 for 90 degrees. And then again, another 1, 2, 3 down for 180. So D should be right there, because we can see the lengths 1, 2, 3, 1, 2, 3 are exactly the same. And then, sorry. All right, go. And then my C, to become C prime, we can measure that it has a distance of 1, 2, 3, 4 away from the origin. So I'm going to count that same way, 1, 2, 3, 4. And it has a height of 2 on the y-axis. So I'm going to count down 2 on the y-axis, 1, 2. So I should have C prime there. And then I'll connect my quadrilateral and make sure that all my lengths are the same. From C to B, I have 1, 2, 3 units, 1, 2, 3. From C to D, I technically cross over 1, 2 boxes, 1, 2. For AB, I have 1, 2. And for D to A, 1, 2, 3, 1, 2, 3. Okay. So this is a 180 degree rotation of this quadrilateral. Let's try 270 degrees. Clockwise now it tells me. So clockwise is this way. This would be 90 degrees clockwise. This would be 180 degrees, whether it's counter or clockwise. And this would be 270 degrees clockwise. Now remember, that changes if you're going counterclockwise, right? It's going to be kind of the direct opposite. And this would be 360 degrees. 360 degrees, just like 180. I don't have to give it a clockwise or counterclockwise directional because it's going to take me back to the same location. So 270 degrees clockwise, I need to end up in this quadrant. The A is going to stay in the exact same location because it is my point of origin, and that's my center of rotation or my spot starting point. 270 degrees, let's start with point B, maybe, right? Point B is here for 180. I need to make sure that point B, continuing off of point A, is going to take me 2 units across, right? 1 unit along the Y, 2 units down. So I need to make sure that my length is going to be 2 units for B and up 1. So B with 2. For C, this is 180 degrees. To go another 90, I need to make sure that my distance from B to C is how much, instead of trying to figure out each coordinate. 1, 2, 3. So I need a distance of 1, 2, 3 for C. And then for C to D or A to D, I have a distance of 1, 2, 3. 1, 2, 3. All I did was count from A to D my distance, and I know D, the line segment AD, has been sitting on top of these x-axes and y-axes, so it's going to need to stay that way. These two are going to need to stay on an axis because that's how they started, right? So I would just measure the distance from A to D, 1, 2, 3 units, just like it is everywhere else. Then from point A to point B, I had a distance of 2 on the y-axis and 1 on the x-axis to get to this point. So I needed to flip it and say now it's going to have a distance of 2 on the y, 2 on the x, and 1 on the y. So it's there. And instead of trying to figure out how C works, I would count the units from B to C. 1, 2, 3 units, 1, 2, 3. And I connect the dots. So what are the coordinates of point C after a 90-degree clockwise rotation followed by 180 degrees? That's basically saying where did it end up after 90 plus 180 degrees, which is that 270-degree rotation that we just did. What are its units or quadrants or coordinates? On Y, on X we have 1, 2, but it's a -2. And on Y we have 1, 2, 3, 4. So main takeaways. Gotta make sure that you are figuring out clockwise or counterclockwise, that your point of origin does not change. This A should go nowhere, wherever your starting point is, which in this case is the center of origin or the origin. That should never move off of that. Everything's rotating around that one point. Keep in mind also the distances from that origin to every other piece of your shape or figure. And then make sure that you know every quadrant is another 90-degree rotation. So 90, 180, 270, 360, or the opposite way if you're going counterclockwise. All right? Give it your best shot. Give it a try. Try to do numbers 4 and 5 on the guided practice to kind of help you and look at your answers. But you're going to go ahead and do numbers 7 through 14. Okay, trying your best. 7 through 14. Make sure you use the answer key to help you.